identifier, and read all about it. Appeared this morning. And it's something we've been working on for a while, and I'm quite excited about. So the way I'm going to structure the talk is, I'm not going to say a lot of, I want to prove a theorem to you, but I'm not going to say anything about the actual proof. I'm going to try and sort of set up why you might be interested in such a theorem, and like the ingredients that go into the statement of the theorem. And then I'll say a bit about the construction, but none of the details really. So the theorem itself is a representation theorem, which in general is the kind of thing where you give me some abstract structure, and then the theorem tells me, gee, this abstract structure is really always of this and this concrete form. And typically the concrete form is, there's simple kinds of the abstract thing, and they're put together in some way that we know. So for example, you could think about any natural number is a product of prime numbers. So prime numbers are the simple things, and they're put together in a way we know, namely by multiplication. And that way you can take an abstract thing, the natural number, into a more concrete thing. Or, you know, any finite abelian group is a product of cyclic ones, that sort of thing. So I'm not interested in numbers or groups today. I want to talk about monoidal categories. So I'm going to prove something like any monoidal category has a certain shape. And the shape I want to talk about is, it is always a sort of continuously varying, particularly simple type of monoidal category. So the first couple of slides, I'll go into what I mean by these sorts of words. And I'm going to phrase it in the following way, that categories should be nice and easy. And these nice and easy, I'll try and color code them in the slides. I mean very specific things with, I'll introduce the proper notation when the time is ripe. But just to set the scene, think about the category of vector spaces, which is, you know, maybe not everybody's favorite category, but I know many people's favorite category. So this is a monoidal category, so it has some structure, it's nice. But vect times vect, like the product of vector spaces with itself, is also a monoidal category. But in some sense, vect on its own is easier because it does not decompose as a product. So by easy, I mean these sort of particularly simple types of categories. So the theorem I want to prove to you today says that any nice enough monoidal category is a dependent product of easy ones. And again, I'll explain what I mean by nice and easy and dependent, but think about this setting of vect times vect. This category vect squared is a dependent product, namely indexed over two elements, of easy categories, namely two copies of vect. And moreover, any monoidal category embeds into such a nice thing. So as a corollary, any monoidal category will embed into a dependent product of easy ones, a so-called subdirect representation. By the way, Brendan didn't say this, but microphones are open. If at any point you want to ask a question that's, you know, brief and to the point, please go ahead.
I want to ask why you call it, why is the product dependent? Why do you call it, why not just a product?
In this case, it is a product. I'll get to why I said dependent in a minute. That's a good question.
Yeah, another question. Should it be an automatic thing to replace it with this easy one?
Sorry, I'm having trouble hearing you. Could you repeat that?
Okay, well, I don't. Okay.
Okay, I'll just push on. Maybe we'll get to that later. So think again about this product vect times vect. So it's a product of vect with itself over an index set of two elements. And that's decomposable because this two index set, two element index set is a disjoint union. Right? That's precisely what it means to be decomposable. So it turns out if you give me the category vect times vect, you don't tell me that it's a product of categories. I can reconstruct this two element index set by the so-called central idempotents. And this is going to be the central notion in the talk today. And I'll explain exactly what I mean by these. But now I can say a bit better what I mean by nice and easy in terms of these central idempotents. So think about the central idempotents as, you know, the indexing set over which the product is taken. And we'll call a category nice if these central idempotents behave well. So this can take two forms, like a weak form and a strong form, nice and very nice. The weak form I'll call stiff, that means that these central idempotents, they form a semi-lattice that's respected by the tensor product. And the very nice form I'm going to call having universal joins. That means these central idempotents don't only have meets, they in fact have all joins, all greatest upper bounds of all sets. Least upper bounds of arbitrary subsets. And again, I want them to be respected by the tensor product. So that's what a category, that's when I'll consider a category to be nice, right? When the central idempotents behave well. And I'll consider it easy if it is what's called sublocal. So that means if you think about these central idempotents as a partially ordered set, which they are, then being sublocal means that any finite cover contains the open that is covered. So let me unpack that for a bit. So I think about the elements of the partially ordered set as open sets. I think about a cover as something that's above a join of a number of elements you give me a number of elements that I think about as opens. It has a supremum that I'll call its cover. And it's local if whenever that happens, one of the opens is already equal to that supremum. So if you think about a topological space, for example, you look at the open subsets of a fixed topological space, they form a partially ordered set. What does it mean for that partially ordered set to be local or sublocal? It means exactly that there's a single point in the topological space, that's a so-called focal point, whose only neighborhood is the whole topological space. So in other words, any net whatsoever converges to that single focal point. So that like single point determines everything, so to speak. So in that sense, a category is easy when its central idempotents look a lot like a singleton set space. Or you can think about it in a logical way. If you think about the central idempotents as the partially ordered set formed by them as a Heunen algebra, for example, then being sublocal, being easy, means the disjunction property, which says that if A or B holds, then either A holds or B holds. That sounds a bit like a tautology, but that's really the crux of doing things constructively. If I can prove to you that A or B is true, then I better give you a proof of A or a proof of B.
And just to clarify, when you say central idempotent, you're referring to an automorph, like a functor, an endofunctor, correct?
Not quite, but I'll get to that in more detail in a minute. I'm just trying to give you an intuition for what I mean at the minute. On this slide, I just want to point out that I'll put sometimes sublocal as a sub of sublocal between brackets, because I want to make a difference between finite covers and arbitrary covers. The same with joins here. Sometimes I'll say finite joins, then I mean it's only finitely complete. It doesn't really matter for the story, but you can make a difference in these things. So just to recap, every monoidal category, I'll prove in a minute, has this notion called central idempotents. We'll think of the category as nice in two ways, stiff or having universal joins when these are well behaved. And we think of it as easy when these central idempotents are a lot like a singleton space, when it's sublocal. Okay, so those are, if you go back to what I promised to prove you, are like the green and the orange things. And now I promised Ronnie that I'll talk about what dependent products mean. And I said dependent products because it could happen that, so here we had vect times vect, and both of the fibers of the representation are just equal to each other. They're both just vect. But it could happen that the fibers, of course, depend on the I. So in that sense, they're going to be dependent. And in fact, I want them to continuously depend on that index. So I'm going to talk about sheaves. I know not everybody is up to speed with them, so I'll give you a short, brief introduction to them. Think about sheaves as continuously parameterized objects. The way to do this rigorously is you start with a topological space, X, and you say a pre-sheaf on this space is a functor that takes an open set and an open subset of the space and assigns to it some set. Could be anything, as long as if you go to a smaller subset, there's a function to the going out to the other space, to the other set. So here's a horribly inaccurate picture, but that helps with the intuition a bit. If I think about the topological space X as being one-dimensional, so being this line here, and I put the whole category set here on the vertical axis. Let's look at these two opens U and V, open subsets of X. So to U, some set is assigned, f of U, called the local sections over U typically. And to V, some set is assigned, f of V, the local sections over V. Now U is included in V, U is smaller than V, so we have to have a map going the other way that takes a local section over V and turns it into a local section over U. And this is called restriction typically. Also, the whole space itself, X itself, is of course open. So there's also a set attached to X itself that we'll call the global sections. Okay, so that's a pre-sheaf, but I said a sheaf is something that's continuously parameterized. So to make that precise, a sheaf is just a continuous pre-sheaf in the sense that it preserves limits, categorical limits, from this category, the frame of opens of the space to set. But notice this thing is contravariant, so limits in the domain turns into co-limits. So continuity means that f turns a co-limit of things into the limit of the f of the things. Now, if I unpack what this says, because these things are sets, and this is a limit of sets, and we know exactly how to compute limits in the category of sets, namely, they're an equalizer of a product. So on the left here, if I take a bunch of open subsets, their co-limit is just going to be their union. I take the f of that, so I can think of those as global sections. On the right here, if I work out what this limit means, you get local sections over each of the opens, such that they are compatible on intersections, which is what this formula here says. So a pre-sheaf is a sheaf exactly when global sections are in bijection with families of local sections that are compatible. So in the sort of picture that we had on the previous slide. Now think about one specific pre-sheaf that assigns, so I've taken as a base set here the real numbers. I still have two opens U and V. Think about the pre-sheaf that assigns to the open set U the set of continuous functions from U to R. So here is one such thing, the magenta one. Here's a continuous function from V to R, this purplish one. What this formula here says is these two things are local sections, and in the intersection, they do the same thing. So they are compatible in that sense. So if I have two such compatible, a family of such compatible local sections, I can glue them together to a global one. That's the sheaf condition. So that was about sheaves in set, but I told you I want to have a representation theorem for monoidal categories. So I'm not going to have sheaves with values taking values in set. I want my sheaves to take values in monoidal categories. So then, how do I phrase this sort of thing? I can still write down what this means, but now I can't talk about elements of the set FV. So instead, what you have to do is you rephrase this, working out what the limit on the right-hand side of the sheaf condition is here. And it means now that this diagram here becomes an equalizer, not in sets, but in the category of monoidal categories. I won't read it out entirely to you, but it says that, so the thing in the middle here, these were sort of local sections, and there's a whole product of them. So these are just families of local sections with no conditions on them whatsoever. And these two functors here say exactly that they are pairwise compatible, that if two open sets overlap, then on the overlap, they do the same thing, these elements of the families. This thing on the left here is the global sections. So it being an equalizer means exactly that global sections are in bijection with families of local sections that are pairwise compatible. And this is something you can phrase not just for sets, but for an arbitrary category. So I'm going to take functors f, sheaves f, to take values in monoidal categories. And this is what it means to be a sheaf of monoidal categories. And the last thing I need to tell you in the little intro about sheaves is about stalks. So far I've told you that you have some base space X. It has open sets. And what the sheaf does is it assigns sets of local sections to this open set. But if I have an actual space, this space also has actual points. So what you can do is you can look at all the neighborhoods of that point. So here U, V, W get smaller and smaller and smaller around this point. You also get sets of local or categories of local sections attached to these open sets. They get in the picture smaller and smaller and smaller. And if you take that co-limit, you're left with sort of the line over X, and that thing is called the stalk. So the stalk of F at the point X is the co-limit of all the local sections where the open ranges over all neighborhoods of the point. And when I'm going to say later on that we have a sheaf of something, 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 then I mean a sheaf whose stalks satisfy the something, something. So for example, when people talk about a sheaf of local rings, that means it's a sheaf of rings and all of the stalks are again rings, but moreover, they're local ones. So this is where the easy thing comes into play. Okay, that's enough about sheaves. Now I can tell you a bit about what I'm actually going to prove in more detail. So from the literature, there are several results, representation theorems in terms of sheaves. For example, if you start with a Boolean algebra, then Stone's theorem, representation theorem, says you can always, this is always in bijection with the global section of a sheaf of spaces, where the spaces are all two valued, or like the simple Boolean algebra with two elements, true and false, if you like. Maybe the most prototypical example of such a thing is if you start with a ring, use the ring, any such thing is in bijection with the global sections of a sheaf of rings whose stalks are local. Right? So any ring is the global sections of local rings, or a sheaf of local rings. And more generally, if you start with a topos, this is very appropriate talking about this in the Topos Institute Colloquium. Any topos you can prove is always equivalent to the category of global sections of a sheaf of not just toposes, but toposes that are local, where the stalks are local. And again, I'll remind you that local means that they're sort of easy in the sense that their truth values are sort of like a singleton space, that they satisfy this logical disjunction property. So those things are known from the literature, but what I'll try to prove to you today is a new theorem that encapsulates, that subsumes all of these, that says if you start with a monoidal category that has universal joins, which all of these things do, then as always equivalent to the category of global sections of a sheaf of monoidal categories whose stalks are local. Right, so we started with a monoidal category. That's the abstract thing I want to represent. I've broken it down into particularly simple types of monoidal categories, namely local ones, that are glued together in a way that we know about, namely via sheaves. So they're sort of continuously varying local monoidal categories, if you like. And then as a corollary of that, I'll prove an embedding theorem. I'll talk about an embedding theorem that says if you start with a stiff monoidal category, so that's like the very weak form of being nice, if you remember, you can always embed such a thing into a monoidal category with universal joins. So a nice category, like weakly nice category, I can always freely complete to a very nice monoidal category, which we know by the theorem has this nice form. Okay, so that's what we're all about. Now let me get to some more details. So somebody was asking about the central idempotents, what I mean exactly by that sort of thing. So if I'm going to prove a representation theorem like this, it has to hold in particular for the category of set value sheaves over a space, right? So if somebody gives me the actual category of sheaves over X, but doesn't tell me that it's the category of sheaves over X, they just give me the monoidal structure of it, I have to be able to reconstruct the opens of it. And that's the role of these central idempotents. So in the category of sheaves, I can write down a certain algebraic notion called central idempotent that is in bijection with the open sets of X, open subsets of X. But this algebraic condition works in general for any monoidal category. And what is this algebraic condition? Does somebody want to ask a question there? Or somebody was just sneezing. So what is a central idempotent? Well, by that I mean it's a morphism into the tensor unit, the monoidal unit I, that comes with something called a half braiding. So I'm not asking that my monoidal category is braided or symmetric, but I will ask that a central idempotent comes equipped with a natural transformation from U tensor blank to blank tensor U. That satisfies some properties that I didn't write down, but that mean that this thing is what's called a half braiding. If you're familiar with the Drinfeld center of a monoidal category, this is an object of the center. So in this sense, this morphism is central. But I want another notion of central, and that's a bit tied up with being idempotent, because by idempotent, I mean that if I take the domain of this morphism, big U, I tensor it with itself, I want that thing to be isomorphic to U itself. So U squared is U as objects, if you like. So in that sense, idempotent. But not just any isomorphism. I want this canonical map to be invertible. And which canonical map is that? Well, I start at U tensor U. I do little u to the right copy and turns it into a tensor unit. I forget about the tensor unit. I'm left with one copy of U. Another thing I can do is I forget about the left copy of U and keep the right one. So those are two maps from U times U to U. I want both of these maps to be equal, and I want them both to be invertible. So altogether, this is what I'll call a central idempotent, a map into the tensor unit that is central in this sense and idempotent in that sense. So to make this a bit more concrete, I'm going to use the graphical calculus on the right here in gray, where we write down the morphism little u as this little dot that starts with, on the bottom here, at with an input from big U and ends with an output in the tensor unit that you just don't see. Then this half braiding looks like this, just like a braiding where you can swap A and U. And the fact that this canonical mapper is invertible means it has an inverse. So there is a map that goes the other direction that I'll draw as this little dot with one in and two out. Now what the conditions mean that I wrote down on the left is the fact that these two things are equal becomes this picture. I started with two copies of U. Either I throw away the right one or I throw away the left one. I want those two things to be equal. Part of this being this map respecting half gradings means that this picture has to hold. If I start with a U and an A, I swap them around, and then I forget about the U. That should be the same as forgetting about the U straight away. In either case, I'm just left with an A. And finally, the fact that this is the inverse of that becomes this picture here. If I first do the inverse and then, U tensor U, that should be the same as not doing anything. As a side remark, let me just say here that, so there's two notions of central that I'm both demanding. First is that it comes with this half braiding. Second is that throwing the left or throwing the right away is the same thing. It turns out that these two are entangled in a certain way. Namely, you can prove that given the other stuff here, this last condition that it's an inverse is equivalent to the half braiding being the identity on itself. So the half braiding allows me to swap a U with an A, any A, but in particular, if I try and swap U and U, then nothing happens. It's just the identity. Okay, so I hope this answers, I forget who it was, someone's question about what exactly are central idempotents. Maybe you can rephrase them in terms of endofunctors, very probably, but I'm going to use this sense.
It does, but maybe you're about to give the examples. I was just wondering what happens for vect cross vect. Like, what is U?
I was going to give examples right now.
Okay, thank you.
So here's a big table with, on the left, various categories. On the right, what are its central idempotents? So first little lemma you can prove is if you start with a category where a tensor product is actually a product with a Cartesian category, then the central idempotents correspond one-to-one to subterminal objects. So sub-objects of the tensor unit. So in particular, if you take the category of set valued sheaves over topological space X, you recover the opens of X this way. That's good. That's a sort of sanity check. Next example here, if you take a semi-lattice, which means a partially ordered set where you have meets, right? Binary greatest lower bounds. I can think about such a thing as a monoidal category where the objects are elements of the lattice, the ordering gives me morphisms, and the tensor product is given by the meets. Then every object whatsoever is going to be a central idempotent. And for people that know about quantiles, which is a sort of non-commutative version of this, if you like, if you start with a quantile, ask what are its central idempotents, you end up with the largest subframe of elements that are below the multiplicative unit and are idempotent, literally in the multiplicative sense. But maybe more interesting to the vector spaces case, if you start with a commutative ring, it could be non-unital, but you need to take some pains to make everything well defined. But take a commutative ring, look at the category modules over it. What are its central idempotents? I'm sorry, I take the usual bilinear tensor product on it to make it monoidal. What are the central idempotents? So they will include at least the ideals of R that are idempotent in the sense of if I take the ideal product of the ideal with itself, I get the ideal itself. So those are central idempotents. There could be more. I don't have a one-to-one correspondence here, and I'm interested in finding out what exactly happens, but my algebra is too weak for this. So if anybody has ideas, please let me know. However, if you start not just with an arbitrary commutative ring, but a ring with some more structure on it, for example, you take a bi-algebra over a field, so for example, a Hopf algebra or a quantum group, and look at its modules under the usual tensor product, then the central idempotents are exactly the central idempotent elements of that bi-algebra. And I'll point out here that the bi-algebra does not need to be commutative. The central is sort of comes out. Another variation on modules on a ring you can look at is if your ring happens to be this C-star algebra of continuous complex valued functions on a locally compact Hausdorff space X that vanish at infinity. That's a ring. You can look at modules over that ring. And in fact, you can look at Hilbert modules over that ring. So what that means is you take the definition of Hilbert space, which is a vector space with an inner product, where the inner product takes values in complex numbers usually. You take that definition, everywhere you see complex numbers, you replace it with this. So now the inner product doesn't take values in complex numbers, it takes values in this ring. And the whole thing is a module over that ring. So that's a nice monoidal category. If you ask what are its central idempotents, you again recover the opens of X. But let me point out here that this is very much a linear. So when we said sheaves over X, that was Cartesian, right? The tensor product was in a sense boring, it's just a product. This is a real tensor product. And even more, this is not anything like an abelian category. So this is really a sort of analytic thing, and still this algebraic condition of having central idempotents gives the right thing, you could say.
Just to clarify what this means, when you say this reproduces the opens of Fx, you mean each such central idempotent looks like C naught of U for some open set U and X?
Yes, exactly.
Okay.
Or is bijective with isomorphic to that thing. The last example isn't very interesting, so I'll skip that. Okay, so some basic properties. I was telling that the central idempotents form a semi-lattice always. If I give you two central idempotents U and V, you can just take their tensor product. In terms of pictures, I can take the little things with the dots on them side by side. I get another thing to the tensor unit, which is again, you can prove a central idempotent. And that makes them into a semi-lattice. So that means they're automatically ordered. You say one is below another if the meet of the two is the smaller one. In terms of diagrams, commutative diagrams, that means here's the one that we're calling the smaller one. There's the other one that we're calling the bigger one. It means exactly that the smaller one factors through the bigger one. And in terms of pictures, graphical calculus, I'm going to draw that as this. Here's the one that we're calling the smaller one, starts at U and forgets about it. Here's the other one that we're calling the bigger one, starts at V, forgets about it. There's this mediating map between them that I'll just draw as another dot that goes from U to V. It's unique as well. So in those kinds of terms, I can now say exactly what it means for a category to be nice. remember that means that the central idempotents are well behaved in three various stronger ascending strength. So I'll say C is stiff when this thing is a pullback. And I realize now that it's not exactly clear what the pullback square is. So let me show you that. I'm going to swap to a different app because I made these slides on an iPad, and the kids are playing Minecraft on the iPad now, which is a great use of university machine, but I need to use some different drawing software. So if you have two central idempotents, here's one, there's the other. They both go into I. I can take that tensor product, and we said that that thing is its meat. So what you do here is you forget about the V. What you do here is you forget about the U. And I'll just not bother with coherence isomorphisms for now. So this being the meat means that that is a pullback, this square. What being stiff means is that I want to be able to tack arbitrary objects onto this. So if I have an arbitrary object, I took it here, I put it there, I put it everywhere. And that doesn't fit. Then I still want this to be a pullback. So if I draw this in pictures, the path along the top looks like this. I start at a U, V. The path along the top forgets about the V. Path along the right forgets about the U, and the A just survives. Whereas if I take the path along the left first, that forgets about the U first. And then the path along the bottom forgets about the V. So this is what I mean when I say I want this to be a pullback. The same way I can ask that there's universal joins or finite joins, by which I mean, let's say finite joins. I want the central idempotents to not just be a semi-lattice, but actually a distributive lattice. I want them to have joins, binary joins. And I want this square that I was just drawing, the analogon to it, to have not just be a pullback, but a push out as well, because now push out is a bit like the joins. That's the binary part. And then there's another part that says I want it to be an initial object, such that tensoring with the initial object is again initial. And then you can sort of do an infinite version of that as well. Okay, so that's exactly what it means for a category to be nice, to have universal joins or finite joins. Let's move on. So the first, like the corollary I promised you, said something like if you start with a stiff monoidal category, so that's the very weakest form of being nice, and basically every monoidal category that I know satisfies this property. I only know one counterexample, and it's very artificial. So if you start with a stiff monoidal category, I can make it nicer. I can really complete it with universal joins, or universal finite joins. So I can just throw these things in a universal way, which I mean the following. You give me a stiff category C. I make a new category D of C out of it, in which C embeds by a strong monoidal functor. The new thing will have universal joins in such a way that if you give me any other category with universal joins and any functor into it, that preserves the right stuff that I'll get to in a minute, then this factors uniquely through this universal category I built through a functor that preserves the right kind of stuff. So what does the functor need to preserve? It needs to be lax monoidal. So that means for any two objects A and B, it has to be a map from FA tensor FB to F of A tensor B. But I wanted to preserve central idempotents, so I have to put some structure at least on these maps. I'm going to say that these coherence maps, if you start with A and a central idempotent, I want it to be iso. And I want, if you start with a half braiding and apply F to it, I want it to extend to a half braiding again. If your category C was braided, then the last thing is automatic. Okay, so this means if we're interested in monoidal categories with this very weak niceness conditions on it, we can always complete them to have like the very strong forms of niceness on them, and we can restrict our attention, if you like, to the extremely nice kinds of categories. So from now on, I'm going to be talking about monoidal categories with universal finite joins, universal joins. Okay, now I'm going to start on the construction of the actual main result. This is the sheaf representation. So you give me a monoidal category with universal finite joins. I'm going to build a sheaf of monoidal categories out of it. So to build a sheaf, I first have to tell you on what space I'm going to build the sheaf. What is the base space X? So what I'm going to do is I take the central idempotents of the category you gave me, and I take what's called its Zariski spectrum, which means you take its completely prime filters of that semi-lattice of central idempotents, or even frame of central idempotents. And let me just briefly say what this means. If you have a topological space X on the left here, the purple thing, and you're just given its opens, you're just given the topology itself, right, the family of open subsets, how can you think about points? So this point X here, I'll think about this as the family of all its neighborhoods. And if the space is nice enough, that completely determines the points. So this is like in a topological picture. Here's a sort of Hasse diagram where the partially ordered set of all open subsets with X is the largest open subset, empty set is the smallest one. Here's UVW, sort of going smaller and smaller and smaller. They all contain X. And this like upper set here, this completely prime filter, is all the subset that contain X. So if singleton X was open itself, then it would just be all the things greater or equal than X. But in general, X itself, won't be an open subset, won't be in here. So we have to talk about these completely prime filters. Okay, so that's the base space. You start with the central idempotents and look at the completely prime filters. Now I'm going to start building the sheaf on them. So remember, a sheaf is to each open subset. So in particular, it's good enough if to like a basic open subset, these things, the central idempotents themselves, I have to assign a category, a monoidal category. And this is what I'm going to do. As objects, I'm going to take the same objects as C, as the category you gave me. But as morphisms from A to B, I'm going to take maps in C of the form A tensor U to B for this fixed U. So in the kinds of irresponsible, unpedagogical pictures we had before, where the axes don't really mean anything, it looks a bit like this, right? If we put the base space X on the horizontal axis, then there's some subset U here that we're talking about. In a sense, we want to think about the objects of C as assigning something to open subsets of open subset U. And these sorts of morphisms, what they do is they sort of restrict the object A and B to only live over U. So sort of cut away everything to the left and right of U in this picture. But don't take that too seriously. Concretely, what we're going to do is take morphisms from A times U to B. Then I have to tell you how this becomes a category. So for example, I have to tell you what the identity is. So the identity from A to A in this in this category of local sections is going to be a map from AU to A in the base category. I'm going to take this one. I just forget about the U. How do I compose two maps? So if you give me a map from A to B and a map from B to C, then what I do is I first copy the U, which I can do because one of the conditions of being central idempotent is that this inverse exists here. I can copy things around. I feed one copy into F, I feed the second copy into G. So that's how you compose. And similarly, you can take tensor products by taking F, taking G, putting them side by side, copying the U, because you need one input for F and one for G. And here you need the half braiding. This is really the only reason why I'm asking for the half braiding, to make this category of local sections monoidal again. So that's the category of local sections I'm going to attach to a basic open subset, to a central idempotent. For people in the know, you can think about this as the Kleisli category of the monad Lang tensor U. And in the Topos case, if you're in a Cartesian category where the tensor product is an actual product, this thing is equivalent but not isomorphic to the slice category of C over U, or the over category C over U. But anyway, this is my definition of the local sections. And now,
Something?
yes, of course, go ahead.
So U was a prime filter on this space, but it's also an object of C. So is there some kind of correspondence between these prime filters and objects, or they're not understand?
Sorry, I skipped over that a bit because I saw time is running. So we
Sorry.
start with central idempotents. So these are, the morphisms little u from big U to I. They form a frame, a distributive lattice. And of that frame, I'm going to take the completely prime filters. So one way to think about this is the elements of the frame, like the central idempotents, they form the basic opens. They form a base for the topology. And then the completely prime filters just generate the topology out of that. So it turns out that if you want to define what a sheaf does, what a pre-sheaf does, it's good enough to define it on the basic opens. So that's what I'm doing here. So officially, you need to extend this from U to completely prime, all opens. So I hope that answers that. And that's a good point because here I need to say something about that anyway. So I've defined what the structure pre-sheaf is. I have to prove to you the sheaf condition, which is that it sort of varies continuously. That comes down to this thing being an equalizer. So I look at the local sections over U join V, going into the product of the local section over U and the local section over V, that both restrict to local sections over the meet of them. So think about them as pairs of local sections that overlap as before. And you can just prove that this is an equalizer. So the structure sheaf is in fact, pre-sheaf is in fact the sheaf. So that's great. And the last thing I need to prove to you is, so now we've proven that, well, I haven't proven, but I'm claiming that the monoidal category you gave me to start with is equivalent to the category of global sections of this sheaf. I have to prove to you that the sheaf is one of simple, easy things. So in other words, that the stalks are local or sublocal, depending on whether you want finite. And the stalks, remember, are the co-limits of the things restricted to U, where U runs over all neighborhoods of that point we're interested in, the point X. So you can prove that this co-limit looks as follows. It's equivalent to this concrete category that I'm about to define. And then you can prove that this concrete category that I'm about to define is in fact local. So what's this concrete category? Again, as objects, I'm going to take the very same objects as the category we started with. As morphisms from A to B, I'm now going to again take maps from A tensor U to B, but now not for a fixed U, but for any U that contains the point X. And I'm going to identify two such things when, so a map F and a map F prime going from AU to B and AU prime to B. I'm going to identify them when there's another open V that's below both U and U prime. So it could be the intersection of the two, for example, on which they do the same thing. So if you know a bit about sheaf theory, this is the monoidal version of what it means to be a germ of a function. How do I compose these things? Well, it's almost the same as before. I have an F and a G, except now F is something that lives on U and G is something that lives on V. So I'm just going to compose them as before, but the result is going to live on the intersection of U and V, which is allowed, right? Because the U in the definition of morphisms is allowed to vary. So you can define this concrete category. You can prove it is the co-limit, it's isomorphic to the co-limit, and you can prove it's sublocal. So that's the end of the proof. Now we're happy. So what have I've skipped over all the details, of course, but what we've seen so far, and this is the main result, we're very happy with this exclamation mark here. If you start with a stiff monoidal category, so that's a nice one in a very weak sense, you can always make it very nice in the sense that you can complete it with universal finite joins in a universal way. And such a very nice monoidal category is always equivalent to the category of global sections of sublocal monoidal categories. So it's a mouthful, but hopefully by now you understand what I mean by that. So that's the theorem. It holds for arbitrary monoidal categories. Well, they have to be stiff. So we can apply it to various monoidal categories now and see what happens. And that way we recover various results from the literature. For example, if the monoidal category you started with was in fact a topos, then the sheaf representation that I've given you is exactly the one from the literature in toposes, which I attach to the names Lambek-Moerdijk-Awodey, but I'm sure there's many more. But now we can also apply to things that are not toposes or not even Cartesian. For example, if I start with a Boolean algebra, you give me a Boolean algebra, I can regard that thing as a monoidal category by saying objects of the category are elements of the Boolean algebra. The meat becomes the tensor product. The less equal becomes the morphisms. The theorem applies to that too. So again, I get this sort of sheaf representation of a Boolean algebra, and the one you get is exactly the stone representation theorem of a continuous field of sets of truth-valued sets. Another thing I can do is, if you give me the category of Hilbert modules that we talked about a bit earlier, which is not a topos and not a Boolean, but it's still a monoidal category. So I can apply my theorem to it. It is equivalent to the category of global sections, also sublocal monoidal categories. And that's exactly what's called Takahashi's representation theorem in this field of Hilbert modules, because you can prove, what he did is to prove that any Hilbert module is equivalent to what he called a continuous field of Hilbert spaces, which is exactly the kind of thing we're trying to do, right? Because, you know, a Hilbert space, the category Hilb itself is easy, is simple, it's local. And then you have a whole bunch of them lying over some base space, but varying continuously. And finally, if you start with a commutative ring and look at modules over it, so this is a setting that I'm not completely worked out yet. But one thing you can do is you take the Peirce spectrum of that thing, including the idempotent ideals. And then the sheaf representation theorem says a similar thing. Any module corresponds to a global section of a sheaf of modules over simple modules over commutative rings over its Peirce spectrum. So that's cool. I'm very happy with that. Now let me briefly look at the time. And let me give you 2 slides on some properties of this representation theorem. First one about preservation. So you can give me any monoidal category as long as it's stiff. But what if that category has some more structure? Can we say, does the representation then become extra nice in some sense? And the answer is yes, as this theorem here shows. So for example, if you give me a monoidal closed category, then all of the local sections and all of the stalks are also going to be closed. And all of the restriction maps are going to be morphisms of closed categories. Similarly, if you give me a monoidal traced category, a traced monoidal category, then again, the local section and the stalks inherit that property. Or if you give me a compact category in the sense that every object has a dual, which is sometimes associated with this sort of picture. Again, that descends to the stalks and the local sections. And let me just point out that these 3 properties here are very much non-Cartesian properties. They're really about tensor products. If you give me a category whose central idempotents are not just a semilattice, but a Boolean algebra, so they have complements, negations, then the local sections and the stalks are also Boolean algebras. And in fact, you can prove that the stalks are not just any Boolean algebra, but the Boolean algebra with 2 elements, true and false. And then a bit more generally, if you give me a category with a certain shape of limits, let's say J-shaped limits, then the local section and stalks also have J-shaped limits. For co-limits, it's slightly less pretty. If you give me a category that has J-shaped co-limits, I'm going to have to ask that they are projective, in the sense that if I tensor the diagram, the J-shaped diagram with you, with the central idempotent, and then take the co-limit, that's the same as first taking the co-limit and then tensoring. But if you look at these sort of projective J-shaped co-limits, then that descends to the local sections. If you want to go all the way to the stalks, yeah, I have to insist that they are finite, otherwise I don't know how to prove it. So lots of nice properties are preserved by this representation. And the final thing I want to say is, so far I've started with one monoidal category. I've shown that it has a certain nice shape. But this whole representation is functorial as well. If you give me the right sort of morphism between monoidal categories, I can give you the right sort of morphism between the sheaves of monoidal categories, and this is an equivalence of a duality of categories. So let's be slightly more precise here. So on the left here, I take the category whose objects are monoidal categories with universal finite joins. The morphisms, we talked about this a bit earlier, are going to be lax monoidal morphisms that preserve the braiding that preserve the half braiding and that preserve central idempotents. On the other side of the representation, what do you get? Well, as objects, we saw you get sheaves of monoidal categories over some base space X, whose stalks are sublocal. Right, that's what we've shown so far. In fact, a bit more is true for this kind of sheaf, the concrete sort of sheaf that I showed you. Namely, they are flabby. So that typically means, if you think about set valued sheaves, if you have a local section, you can always extend it to a global section. Now, these are not set valued settings we're in, so I can't just talk about the restriction map being surjective. I have to categorify this in the right way. So by flabby, I will mean these objects that I'm interested in. They don't just have restriction maps going this way. This has a left adjoint, a sort of extension map, such that if I have two opens, U and V, U below V, if I take a local section, extend it to something on a larger subset and restrict it back, I get something equivalent to what I started with. So not actually equal, but equivalent, in the sense that the unit of this adjunction is an iso. So the objects are these kinds of flabby sheaves of local monoidal categories. And the morphisms are sort of what you would expect coming from algebraic geometry. They're a continuous function between the base spaces, a natural transformation of the right type between the sheaves, such that the induced stalk maps are conservative on central idempotents, meaning that if you give me a central idempotent in the stalk, it gets mapped to 1, then the thing already itself had better be 1. So if I take these morphisms and these objects, then I get a nice duality of categories. And that's where I'd like to leave it. So just to conclude, I've shown you this sheaf representation theorem, which in a sense cleanly separates the spatial and temporal directions of a monoidal category, if you like. Spatial, I mean the horizontal axis I was drawing on all the irresponsible pictures, and temporal and the vertical one in the direction of composition, if you like. This theorem captures more examples than it did before for the Topos representation theorems, because it worked for tensor products and not products. And one thing I didn't talk about, but which is true, is that the proof is entirely concrete. You never have to go to the level of 2 cells and stacks and all that sort of nonsense. I say nonsense, but of course I don't mean that in the sense of abstract nonsense. And then at the bottom here, I've listed some things I'm interested in looking further. For example, these sort of sheaf representation theorems in, for example, Scott and Lambek's book are used to prove completeness theorems and coherence theorems. So they sort of follow from the sheaf representation theorem, not the other way around. And I'm wondering, of course, now, can you do a similar thing for monoidal categories in this way? Also, monoidal categories form models for linear logic. So toposes are models for intuitionistic higher order logic. For closed monoidal categories are models for multiplicative linear logic. So can we say something about the logic of those types of categories using this representation? Then I'm pretty sure there's loads of examples of this sort of theorem happening in algebra and algebraic geometry, but as I mentioned, my algebra is too weak, so I need to either brush up or find someone who is strong in that sort of thing. Things that we've started working on is, I've written causality here. That means if you give me a monoidal category, I can look at its central idempotents and think about it as a sort of space, but it might be much more than a sort of space. Maybe it carries a metric, maybe, I don't know, it could carry all kinds of stuff. Can you sort of categorify this metric now into some structure on the whole category? So one specific thing we're looking at, because it's interesting in physics, is if you don't just have a space, but a sort of space-time, this has what's called a causal space. Does this come from some sort of structure on the whole category? I'm seeing sort of thing for concurrency. So if you don't just have a space, but something like a Petri net or an event structure where things can happen in parallel, and there's a notion of these things cause further things, and these two things are in conflict, so can't happen at the same time. If you have something like that on the central idempotents, does that correspond to something nice in the whole category? And finally, something we start to work on is if you have a monad on a monoidal category, what does that look like if you transfer it over to the sheaf side? So it turns out you get sort of little monads on all the local section and all the stalks, and they sort of glue together in a nice way. And then I'll leave you with some references. Thank you for your attention. And if you have any questions, now is the time.
Thanks, Chris. Really fascinating talk and great results. Sorry, I need to get to another room. There's a bit of an echo. Does anyone have any questions?
Just like to say, I'm the worker in homotopy theory, using monoidal categories. Can you hear me?
Barely, but I'm making it out. So
Anyway,
homotopy theory and monoidal category.
Homotopy theory, now algebraic topology, and using the monoidal categories in those to model homotopy types. And people always talk about homotopy groups, but the interesting thing is modeling homotopy types. You know, you want to know what do these things look like? Why is it that low-dimensional identifications in spaces produce high-dimensional invariants? What's the algebra which makes sure that that happens? That's the sort of generalized real problem in homotopy theory. But you have to work much more generally. One of the sad things in homotopy theory is to talk about spaces with base point, which is a very restrictive, and the theorems are often restricted to connected spaces. One of the things I introduced was many base points. Instead of taking the fundamental group, you take the fundamental group point with many base points. This is much more effective, and that leads to higher homotopy group points. Things like that. Anyway, I'm happy to write to look up your references in the archive. If I just look up under Christopher Heunen, then I should be able to find lots of your
Yes, I think the slides will be made available as well somewhere. Is that right, Brandon?
Sorry?
Yeah, I'll get them from you immediately following the talk, and they'll be online at latest early next week.
You can write down the number or the title or something else.
Yeah. I'll send you an email anyway.
Yes, happy to
Give
email
it
that.
my particulars and my website on Groupoids. I've got a website on Groupoids.
Yes, great. Thank you.
If you look up convenient categories in the NCAT lab and look up the history of convenient categories, you'll see that the term, without that term, the use of monoidal categories appeared in my 1961 PhD thesis from Oxford. So I'm I consider myself very much a relic, getting rather beyond things anyway. But I think that was 3 years before the this conference on monoidal categories. Yeah, I got to go to the supper now. Thank you very much. Good to hear more.
You.
Okay. At this point, unfortunately, we need to end the live stream, but the room will remain open for further discussion and questions. But before we end the live stream, just thank you again, Chris, for the excellent talk.
Thank you very much. My pleasure.